Hello guys, am I audible and visible? Can you see me and hear me properly? Can anyone confirm whether you can see me properly and hear me? Guys, can you see me and hear me? Am I audible and visible? Okay, fine. I got the answer now. I mean, I was a little bit worried whether you can hear me or see me or not. Welcome to Career Avenues. In today's webinar, we are concentrating upon revising whole of the geophysics topic, and it's a huge chapter, but we will try to revise all the elements of it, and we will see what kind of questions can come in the examination. In the way we will discuss about different questions which can come in the examination and how to answer these questions. So without any delay, let us begin our discussion. Welcome everyone. Welcome. Okay, so let's first see what are the topics we are going to cover today, and then we will go to individual topics. So in the geophysics, our topic is today the geophysics, and especially for the geology students, which will be giving the GATE examinations on the next February. So we will be discussing specific to the GATE subjects, GATE and the geology background GATE. We'll be discussing the three field methods. One is the gravity, electric, and magnetic. Three field methods first we will discuss. After this, we will discuss regarding the electromagnetic survey. The electromagnetic and different kinds of electromagnetic survey we can come across. Next, we will discuss regarding the seismic survey. The seismic survey and seismicity inside the earth, we will discuss about that. Next, we'll discuss about the radiometric survey. And geothermal survey. So these are the field, these are the methods we will going to discuss. Three field methods, these three, gravity, electric, and magnetic, they're called as the field methods. And then combining the electric and magnetic methods, we'll discuss the electromagnetism. Then we'll discuss seismic, then radiometric and geothermal. After this, we will discuss regarding the well logging techniques and how the well logging techniques are used to find out different mineral and oil resources. We will discuss about that. Different well logging techniques and different kinds of well loggings we can see. So this is our broad topic of discussion. Let's start from the first one because we have limited time and we will try to cover as much part as possible. So first we will discuss about the gravity chapter. This is a very well-known chapter to all of you. The first thing you should know about the Newton's law, which is very much easier because all of you must have studied the Newton's law in your school days, no? The Newton said that what? So somewhere Newton was sitting in his garden and the apple fell down and he found out the gravity. It is believed like this, no? It is not like that. People did not derive any equations for the gravity before that. Newton derived the equations from the gravity. So he said that the force of gravitation is proportional to the mass of one object, directly proportional to the mass of the other object, and inversely proportional to the square of the distance between them. That means what? Suppose we have two bodies. One is having capital mass m, second body having a small mass m. The distance between the center of these two bodies is suppose r. Let's say this is the r distance between the center of the two bodies, and the force will be equal to, or the force will be proportional to the two masses, directly proportional to and inversely proportional to the square of the distance. Because we are seeing this particular formula that F is proportional to square of the inversely proportional to the square of the distance, this law, Newton's law, is also called as an inverse square law. It is called as an inverse square law. Why? Because it is the force is inversely proportional to the distance square. Now, if I will write the equation, I can remove the proportional sign by assigning a constant. No, so I can write F is equal to a constant. Let me write the constant over here. It will be capital M into small m by r square. If I multiply into constant, all of you must be aware of this concept that how to remove the gravitation, how to remove the proportionality symbol, no? And this constant is called as the universal gravitational constant, taken as the capital G. So the equation becomes G capital M small m by r square. This is a Newton's law of the gravity, no? So F is equal to capital G and two masses product divided by square of the distance between two masses. Now here we have to observe one thing: the gravitational force is always attractional force. That means two bodies will always attract each other. This is the classical mechanics, guys. So this is the Newton's theory for the gravity, which was disproved by the Einstein and his followers, no? So what does the Einstein say? That it is not so. The gravity is basically a field like this, like our in the solar system. Suppose we have a space like this. Let's say this is a plane space. If I will put an heavy object over here, this particular space will be depressed. For example, if you have a bed sheet, you hold it from all the four ends. If I will keep a heavy object at the middle, the bed sheet will fold down. No, it will fold down to the bottom. So if it folds down like this, for example, let's say if it folds down like this, here is the heavier object, it will attract all the smaller objects towards itself, no? All the objects towards itself, because the space is curved. The Newton's theory did not consider this curving of the space itself, no? This is a relatively new theory which was discovered in the 20th century, no? So we are not going to discuss about the Einstein and his relativity theory. Our topic of discussion is based upon the Newton's law. So first we discuss about the Newton's law. This is the scalar quantity of the force. All of you must be knowing about the scalar and vector. Vector quantities have directions. Scalar quantities do not have any directions. Guys, before continuing, let me tell you this thing very clearly. If you are not getting anything, stop me at once and ask me the question. I will explain this. Huh? We are discussing a subject of science. There is nothing to be, there is very little thing to be remembered. Everything is to be logically apprehended. No? So if I will write it in the vector form, force would be equal to, I can write the same thing, Gmm by r square, but I am interested in writing the force in the vector form because force is a vector quantity. No, I will decide in minus sign and an unit vector. So this is the equation of the gravitational force in the vector form. What is this? Why this minus sign is given? The minus sign is given because every object tries to come from a high potential to low potential. There is a negative potential difference. For example, let's take the Himalayas. Let's take the Himalayas. Okay, so the Himalayas are like this, and we have the Bay of Bengal on this side. The Himalayas go like this, and there is a Bay of Bengal over here, no? Ocean, Bay of Bengal, and here this is the Himalayas. In the Himalayas, we have the glacier, Gangotri Glacier. It will be somewhere over here at this elevation. Let's say this glacier is melting, water is being produced. Now, if you see over here, it has high potential. We'll discuss about the potential a little bit later. High potential. Imagine in the concept of potential energy. You know the potential energy is no mgh. We call it the potential energy. More the height, more the potential energy. And the Gangotri Glacier is at more height compared to the Bay of Bengal. The Bay of Bengal water level is up to this. Who is at more height? The Gangotri Glacier. That's why the water, as the river flows from the Gangotri Glacier to the Bay of Bengal. So high potential to low potential. Everything tries to come from high potential to low potential. So any object, for example, we can take the object as a tennis ball. Let's say we have the earth. This is the earth. You are standing over here. You are throwing a tennis ball upside. You know, when the ball goes up and tries to come down, the earth is attracting this ball towards itself. Here the potential energy is mgh, let's say mgh. But when the ball is coming down, suppose at this position, here the potential energy will be, let's say mgh dash. The h has decreased. That means the potential energy has decreased. So final minus initial, when I will divide or when I will find out the change in energy, that will be final minus initial. Everything when I calculate the change in something, it is always final minus initial. So between this, how much energy change has happened? This mgh dash, I can write mgh dash minus mgh. This much energy change has happened, and this much potential energy change has happened. This means what? This will be negative quantity because mgh dash will be less than mgh because h dash is less than h. No, that's why the negative symbol is given, because the gravitational force is acting in the direction in which the potential energy is decreasing. And this r vector, this little r and a cap is given, called as a unit vector. No, unit vector. It has no magnitude. The magnitude is 1. For the unit vector, magnitude is 1. It just gives the direction. So if I will summarize what we have discussed till now, my Newton's law says that F is equal to G mm by r square. In the scalar form, in the vector form, it will be minus G mm by r square into a unit vector. If I will multiply something into 1, the value does not change. No. Similarly, the unit vector r, it only gives the direction to the force. So this is what my Newton's law is. And we have the value of G is universal. It is always true in the cosmic bodies. That is equal to 6.672 into 10 to the power minus 11 Newton meter square plus kg square in the SI unit. You can calculate these units pretty much easily. We know that F is equal to G mm by r square. Whenever you are finding, or in the question it is given, find out the unit of the G. How do I find out? I will write this equation. Then I will write for G would be equal to how much? F into r square by m into m. What is the unit of F? Newton. What is the unit of the art? Meter. I can write meter square divided by. What is the unit of the mass? Kg. 1 kg for this one, kg for this one. So kg into kg will be equal to Newton meter square per kg square. No? So the unit of the G will be Newton meter square per kg square in the SI unit. Or if I will convert it into the CGS unit, that means I can write it as 6.672 into 10 to the power minus 8 in the CGS unit. The unit is dyne, the force is dyne. I can write centimeter square by gram square. This is in the CGS unit. This is in the CGS unit. This was in the SI unit. Okay. So these are the values of the gravitational constant, universal gravitational constant. So this was the force. Whenever there is a force, there must be a field. So we will now discuss about the gravitational field. Whenever there is a force, there must be a field. Field means easily, if you can easily want to know about what is a field, it is basically force per unit mass. So this is basically force experienced per unit mass. So we had a earth. I was standing on the surface of the earth, threw a tennis ball upside. No, this tennis ball has a mass of, let's say, small m. Earth has a mass of, let's say, capital M. How much force this tennis ball is experiencing? That is experiencing equal to this amount of force. No, but how much force and a unit mass will experience? For example, let's say instead of this tennis ball, I am throwing a unit mass whose mass is supposed to be 1 kg. Any object having 1 kg of mass, I'm throwing this. How much force this will experience? This will be equal to how much? G m. This will be 1 by r square, which will be equal to g m by r square. This is equal to my field, gravitational field. So my gravitational field is equal to g m by r square, where m is the capital M, that is the mass of the earth in this case. No, so we had the gravitational force, we have the gravitational field. We can also write the vector form of the field. I can write the gravitational field as capital E. I can add a vector. I can write minus gm by r square, same logic, into unit vector. This will be the gravitational field. Now, we can calculate the potential energy. Potential energy. You know the energy forms like potential and kinetic energy. So when I was standing on the surface of the earth, I threw the tennis ball upside. No, so the tennis ball first traveled this much distance in this way, and while it is traveling upside, it gained potential energy because it is going against the gravity. No, here the tennis ball is going against the gravity. Gravity is acting downwards. The gravitational force is acting downwards, but the force, the tennis ball in this case is going upside. But when it is coming down, its potential energy is decreasing. So potential energy is the energy gained by its position. No, we know the formula, easy formula is mgh. We can also derive the potential energy from the Newton's law. Basically, energy is equal to energy or work done. We can say work done is basically f dot ds integration. No, we know this thing, dot multiplication, f dot ds integration. Suppose we have two vector quantities, v1 dot v2, dot multiplication will produce v1 v2 into cos theta, isn't it? This is the dot multiplication. Dot multiplication of two vectors will give me a scalar quantity. No, so this is a vector, this is a vector, but the dot multiplication is giving me a scalar quantity. Similarly, if I will derive this equation, I can derive it for f dot dr. I can take F as G mm by r square into dr over here. I can take the negative symbol over here, and the angle will be cos 0 degree, because the force is this direction, the displacement is also this direction. We can integrate this and we can find out finally my G mm by r would be the potential energy of the tennis ball which is coming down. So any object which is being attracted by the gravitational force would have this potential energy, that will be minus G mm by r. Minus is basically the due to the direction, but you can also omit the minus sign. You can calculate only the magnitude, that will be G mm by r. That is the potential energy of the body which is coming down. Similarly, we can write about the potential, not potential energy, that is potential, gravitational potential. Gravitational potential. What is the gravitational potential? This is the potential energy absorbed by the unit mass. Potential energy experienced by unit mass. Same thing as the field. So field was force per unit mass. Potential is potential energy per unit mass. For example, if I will write the potential energy equation, it is G mm by r. No, if I will make the small m1 unit mass, what will be the potential energy? It will be G m by r. If small m is 1, if I'm throwing 1 kg object or 1 kg tennis ball to the upside, when it comes down, how much potential it will be absorbing? It will be G m by r, which is called as the potential. So I will write it as potential. Let's say this P, the potential G m by r. So let me summarize till now what we have discussed. We discussed about force. Force was G mm by r square. I'm not writing in the vector form because vector forms are often not required in the examination. For knowledge, it is okay, but when you do numericals, you will calculate the scalar quantity. Similarly, the field was equal to force per unit mass. I will make this mass G mass 1, so it will be G m by r square. My potential energy was equal to G m by r square into r, basically. No, when I'm integrating over a large distance from 0 to r, the dr integration will become r. So r and r square will be cancelled, it will be G mm by r, potential energy. And potential would be equal to potential energy per unit mass, that will be G m by r. These 4 equations all of you should remember. You don't need to remember. If you know the first equation, so let me summarize the points. We have a force, we have a field. Field is force per mass. Similarly, we have potential energy, that is force dot multiplication distance, and we have potential, which will be equal to energy, that is the potential energy per unit. So if you remember only the force equation, you can derive all the other equations quite easily. Now, when the ball is coming down, let's say we have the earth, the ball is coming down. Suppose the ball has a mass of m. It is coming down with an acceleration. So we know from Newton's second law that rate of change in momentum is proportional to the force, and a particular interpretation is force is equal to mass into acceleration. From the Newton's second law, we know this thing, no? So when the ball is coming down, it will be coming down with a force that is equal to its mass into the acceleration it is moving through. But we already know this force is equal to how much? G capital M small m by r square, the gravitational force. That means what? This force and this force must be equal. So I can write MA is equal to G mm by r square, where m and m are cancelled out. I will get what? Gm by r square. That means my acceleration with which the mass is falling down is equal to how much? G into m by r square. Clear? So it does not depend upon the mass of the object. If you throw a 5 kg object upwards when it is coming down, or when a 3 kg object coming down, a 1 kg object coming down, they all will have this acceleration that is equal to, this is a constant, this is the mass of the earth is constant, and r is not dependent upon the body's mass. It is independent of the mass. No? Suppose we have this is surface, I am standing over here, I throw 3 balls, one is having 5 kg, one is having a weight of 3 kg, and one is having a weight of 2 kg. All of them will experience same amount of acceleration. That is this gm by r square. This acceleration is called as acceleration due to gravity. Or simply g. That means I can write g is equal to gm by r square. Can anyone tell me which other equation I have written having the formula same gm by r square? What was the, which parameter has exactly the same formula gm by r square, which we have already discussed? Anyone? I'm waiting because there is some time lag, so you have to wait for my answer too. Let me see if you are getting this or not. Answer, guys. Nobody is responding. So gravitational field, Akash is saying exactly. So the gravitational field. So gravitational field has exactly the same formula as the acceleration due to gravity. Okay. Now, this g value over here, or let's say the units of the g. Okay. We know we can calculate the unit of g from the equation, that is f is equal to mg. No, this is also the equation. So g would be equal to f by m. F's unit is Newton, m's unit is kg. No, Newton is over here. I can also write the equation, that is g is equal to, yes, I got to answer. Lakshmi, it is not gravitational potential, it is gravitational field. I can also write gm by r square, where g's unit is what? Newton meter square per kg square by meter square. No, it is the equation of this is for the g, capital G, and there is another kg over here. No? So kg and kg are cancelled. Meter square cancel. It will be again Newton per kg. So if I will solve this, the equation, you know, it will be meter per second square. No? If I will convert them, it will be, the acceleration is basically an acceleration unit is meter per second square. No? Is the rate of change in velocity. Velocity changes. Velocity equation is meter per second. The rate of change is meter per second, it is meter per second square. Now, in the gravity, or in this gravity chapter, we have multiple units of gravity which we calculate, and these units often come in the examination. There is some unit called the gal, and 1 gal is equal to 1 centimeter per 1 second square. Very, very important. 1 gal is equal to 1 centimeter per second square. 1 meter per second square is equal to how much centimeter per second square? 100 centimeter per second square. And 1 centimeter per second square is 1 gal. That means it is 100 gal. So when we say our acceleration due to gravity is 9.8 meter per second square, it is equal to 980 gal. The conversion from gal. Similarly, we have another unit which is called the milligal. Milligal. Milligal unit is commonly used in our gravitational survey. So 1 gal would be equal to like 1 meter. How much centimeter? 100 centimeter. It will be 100 centigal. 1 centigal would be equal to 10 milligal. No, deci, centi, milli. All of you must have known knowing the unit conversions. No, that implies 1 gal would be equal to 1000 milligal. As we know, 1 meter is equal to 1000 millimeter. No? So this is the milligal. That means if I want to find out how much milligal of acceleration due to gravity an object faces on the earth, you know the value. It is 1.8 meter per second square. We just find out 980 gal. 980 gal means 980 into 1000 milligal. Gal is named after Galileo, the scientist Galileo. This much milligal. There is another unit of the gravity that is called the gravity unit. Gravity unit, or in the short form, it is called as a GU. 1 GU is equal to 0.1 milligal. 1 gravity unit is 0.1 milligal. Now your job is to find out this 9.8 meter per second square is equal to dash GU. This is your job, is to find it out. Pretty much easy, though. You can solve this. Now let's come back to our force, field, and potential energy and gravity or gravitational acceleration. Let's say we have the earth like this. This is the center of the earth, and let's say we have an object having mass m1 at an height. Let's say it is from the distance from the center of the earth. It's let's say r1. Let's say we have another object having m2 mass, different mass, m2 mass, having the same distance, that is r1. We have another mass, let's say it is m3 mass over here, having the same distance from the earth center, r1. Can you tell me what will be the gravitational potential? Gravitational potential for 3 of them. Gravitational potential for m1 would be equal to how much? It is gm by r. Suppose the mass of the earth is capital M, it will be gm by r1. No. Similarly, gravitational potential, I'm writing the short form, for m2 would be equal to how much? Same, gm by r1, isn't it? Potential, see the potential equations. Same for the gravitational potential for m3 would be equal to gm by r1. So even if the mass are different, m1 was not equal to m2, m2 was not equal to m3, even if the masses were not equal, because of their distance is same from the Earth's center, their potential is equal. That means what? Potential is independent of mass. The gravitational potential is independent of mass. Mass of what? Mass of the object which is facing this force or which is experiencing this force. No? That means if I have the Earth like this, if I will join all the points having same distance from its center, it will make a circle. No? If I will make a circle over here, in each point of this circle, if I will calculate the potential, it will be identical because distance is same. Pardon my picture, but imagine the distances are same. That means they will have equal potential irrespective of their masses. Similarly, I can draw how many such circles? Infinite number of circles around the Earth. Infinite number of circles around the Earth. Clear now? This is these are called the equipotential surfaces. That means let's say this equipotential, so let's say this point is A, this point is B. The potential at point A and potential at point B is equal, irrespective of their mass. So when I'm taking this object A to object B, or any object, suppose the object is over here, I'm taking this from A to B, the work done will be zero. Remember the work done concept we discussed, or the energy concept. The Gangotri Glacier, Ganga is coming from high potential energy to low potential energy, or high potential to low potential. When the potential difference is zero, there is no work done. So since there is no potential, the work done taking an object, or I can say work done moving an object on the same equipotential surface would be equal to zero. No work done at all. Okay. Simply we can say this simply in the logic. The force is acting which direction? The gravitational force is acting towards the Earth's center. The Earth is attracting this towards the Earth's center. The displacement is tangential. In this, what is the angle between the displacement and the force? 90 degree. What is the energy or the work done? F dot ds integration, that is equal to F ds cos theta integration F ds cos 90 degree, the angle between the force and displacement, which will be equal to 0 because cos 90 is 0. No, I often give this funny example of you lifting the gas cylinder and walking on the floor. The work done is 0 because you're lifting the gas cylinder upwards. The force is upwards. The displacement is 90 degrees horizontal. The work done will be 0. So this is why moving along the equipotential surface, my work done is 0. Now the Earth's shape, if we will see, shape of the Earth, Earth is an ellipsoid. No, we know Earth is an oblate ellipsoid, or we can say oblate spheroid. It is less ellipsoid, more spheroid, but it is an oblate spheroid. What does this mean? This means that our equatorial region is inflated and the polar region is little bit squeezed. No, so our equatorial radius is equal to how much? 6772 or something like this. No, so basically equatorial radius is more than the polar radius, isn't it? So if I will draw the Earth shape, oblate spheroid. This is the equator. This is the pole. This is the center of the Earth. Let's say this radius over here. This is the radius at equator, and suppose this radius is radius at the pole, and radius of equator would be more than radius at pole. If this is the case, the value of G will be also different because the radius is different. The equation for G was how much? Capital G M by R square. Yeah, no. So if an object is over here, let's say an object over here, another object over here, the two objects, they will experience different acceleration due to gravity or G. Why? Because the distances are different. At equator, it will be equal to how much? G M by R equator square. And in the pole, it will be equal to G M by R pole square. Which is less? Pole radius is less. If this is less, gravity at the pole will be more, no? Because inversely proportional, no? So G at pole is equal to, oh sorry, it is more than G at equator. So if you want to reduce your weight, you go to the equator. Your weight will come less in the equator, more in the pole. No. How much? The gravity value at the pole is equal to 9.832 meter per second square. Gravity value at the equator is equal to 9.780 meter per second square. Now your job is to find out the difference in gravity between pole and equator is dash gal, dash milligal, and dash gravity unit. Find it out, pretty easy. Just subtract the values, two values, convert meter per second square to gal, milligal, and gravity unit. Easy, no? This kind of question often comes in the examination. Now, there is something called as a reference spheroid. Versus geoid. We will discuss about the reference spheroid versus geoid concept. What is a reference spheroid? If you see the Earth's shape now, we can mathematically model the shape of the Earth by an equation. That equation is given as G is equal to 978,031.846 into 1 plus 0.005278,895 sine square phi plus 0.00002346 sine to the power 4 phi. This in milligram. The reference spheroid equation is given by, or the gravity in the reference spheroid equation can be given by this equation, where phi over here is the geodetic latitude. Now they have asked this question before. They will not ask you the formula as such, but they will ask you this phi over here is what kind of latitude. Now all of you know the latitude concept, no? Suppose this is my Earth. Suppose I'm taking the Earth shape as a sphere, for example. This is the center of the Earth. This must be the equatorial plane, no? Suppose somebody is at this particular position. I will draw a line from this particular position to this particular position, and I will find out this angle, phi. This phi is called as geocentric latitude. I am connecting a point to the center of the earth, calculating the angle between them. That is my geocentric latitude. But what is geodetic latitude? Because the earth's shape is little bit ellipsoidal, no, it will be like this, for example. So this is my equatorial plane, will be somewhere here. Let's say this is the center over here. Suppose I want to find out the latitude of this particular object. If I want to try to calculate the geocentric, just connect it with the center. This phi c, let's say phi c is geocentric latitude. Simple. But this is not the phi I have taken in the formula. That is what phi I have taken, geodetic. Now, what is this geodetic one? Let's see. To calculate the geodetic latitude, what we have to do? First, we have to draw a tangent at this particular point. A tangent. Then I will draw a line that is perpendicular to this tangent, and I will see where it is cutting the equatorial plane over here. Now, this angle, let's say is phi d, is geodetic latitude. So geocentric and geodetic latitude. If the earth would be a proper sphere, pure sphere, geodetic would be equal to geocentric, because we know if I will any point on the circle, if I will draw a tangent, normal to this tangent will go through the center. That means geodetic will be equal to geocentric. Because the earth is not a spheroid, the geodetic and geocentric latitudes are different. So for a spherical body or for a pure sphere, what will I see? Geodetic latitude is equal to geocentric latitude. But for earth, my geodetic latitude will be not equal to the geocentric latitude. So in this reference ellipsoid or reference spheroid equation, which can give you the G value at any latitude, if you will put the latitude value over here, but this is which latitude? Geodetic latitudes, not the geocentric latitude, the reference spheroid. The physical expression of the reference spheroid is a geoid. So physical expression of the reference spheroid is my geoid. For example, the mean sea level. It will be my geoid, or suppose a local datum plane. It will be a geoid. Now let's see what is this geoid and what is this reference spheroid. Let's take an example. The Earth's outer surface is undulating. Somewhere there is mountain, somewhere there is ocean. No, so I can draw the figure like this. No? The outer surface of the Earth is highly undulating. No, like this. The reference spheroid, what does it do? It creates a homogeneous spheroid surface. A basically mathematical model like this. It's a reference spheroid, taking the average values of the elevation. So we are going this down, but we are going this up. This is not the correct thing to say, but to imagine what is the reference spheroid, I'm giving you this example. Just averaging out all the shapes protruding outside or the depressed spaces. This is the reference spheroid. But the reference spheroid is not taking into account about the lateral density variations, which is causing these isostatic imbalances. We will see this thing a little bit later in the isostatic anomaly. So reference spheroid is purely theoretical. It's a theoretical thing. We are assuming that the mass of the Earth is homogeneously distributed, which is not the case. Somewhere we have high dense materials, somewhere we have less dense materials. No, there the geoid comes. Geoid is practical. We can see the geoid, like the ocean or sea level. It is in the sync with the isostasy, isn't it? It will not, the isostasy will be completely balanced in the ocean floor. So it is much more practical because it is taking into consideration the lateral density variation. Okay. So this is the geoid and the reference spheroid, the differences. Next, we are going to discuss regarding the gravity correction terms. So what are the survey? Let's say gravity survey. Let's start the gravity survey. So the theoretical parts are this much, and gravity survey, if I will see, what do? I take my gravimeters. The instrument which is used is what? Gravimeter. And we will see different kinds of gravimeters. It is the instrument that measures gravity. Basically, it measures the change in gravity. Okay. Similarly, from the reference spheroid equation, I can calculate the theoretical gravity. From reference spheroid equation, for example, let's say we have a particular location over here. At this location, I want to measure the gravity. So I take my gravimeters and measure the gravity at this particular position. Let's say that is GM, measured gravity. But this particular place has a latitude. No, I can calculate I can draw the tangent, draw the geodetic latitude, and put it in the reference spheroid equation. Find out the gravity. That is my theoretical gravity. No, could you please explain geoid once more? Akash is saying. Geoid is basically the physical expression. We will discuss about the geoid. Little bit. Give me some time. Once we discuss the isostatic anomaly, then you will be clear about the geoid. Just wait for a couple of minutes. So my measured gravity and theoretical gravity. Now, when I will match them, most often they are not equal. There is some disparity between them. That difference is called as the gravity anomaly. Measured value minus the theoretical value. That is called as the anomaly. This anomaly is produced due to the difference between the reference spheroid and the geoid. Reference spheroid is theoretical, geoid is practical. Again, I'm repeating this thing. Once again, we will discuss a little bit later. So what is the procedure? I take my gravimeter to a particular location over here, measure the gravity data. I will compare it with the theoretical gravity data, and we'll see how much difference is there. And I will find the anomaly. And I will find out why this anomaly is being found. What is the reason behind this anomaly? So I have a measured gravity, that is GM, measured gravity. I use the gravimeters to measure the gravity, measured gravity value. Similarly, we have GT, that is the theoretical gravity value, which is calculated on the basis of the reference spheroid. Now, before comparing them, whatever I have measured, it is not the proper measured value. It is with some error. I have to remove these errors. So first, I will apply some correction terms to the measured gravity value. Then I will compare it with the theoretical gravity value. So what will I do? The anomaly would be actually what? It is the measured gravity value plus the corrections. I have to add some corrections, different kinds of corrections we will discuss a little bit later, minus the theoretical value. Now let's see what are these corrections first. So we'll discuss about the gravitational corrections. What are the corrections we see? Terrain correction, Booger correction, free air correction, latitude correction, drift correction, Eötvös correction, these are the correction terms we see in the gravity survey. Now, what is the current terrain correction? Let's discuss them briefly. Let's discuss them. It's a revision class, so we cannot go into the detail, but I will try to explain as much as possible. Let's say you are this is the surface of the earth. You are standing over here. Okay. Suppose this surface is not a smooth surface. Let's say it's an undulating surface. A mountain is there, a valley is there. Suppose you are measuring at this particular point the gravity data. This is the mountain. This is the valley. They are called as the terrains. No. Suppose this is my datum plane. The datum plane, or basically the reference spheroid where it is passing. Suppose the reference spheroid is passing at this particular location. The reference spheroid is passing along this particular location. You are standing over here, measuring the gravity data. Due to the extra mass in the mountain, it is pushing your gravimeter towards upside. No, the gravimeter basically works in the spring principle, which we'll discuss a little bit later. It has a spring. Simply, if I will tell you, spring is there. A mass M is attached. The mass will be experiencing a force of mg at one location. Suppose it is brought to another location. Suppose the g value decreased. What will happen to the spring? The spring will get squeezed. The mass will move upwards because less force is now applied on it. So suppose this is mg dash. For example, more force is applied, the spring will extend, the mass will come downside. No? More mass means more force. That means we know that F is equal to mg. If the gravity changes, the force will also change. That will be evident in the spring itself. Suppose we have the mountain over here. This is the mountain. The mountain has some mass. It will attract the spring towards itself. Why? Because the gravitational force Newton's we just studied. The spring will be squeezed. So the weight measurement will come less, or the G measurement will come less. So you have to add some value with the measured value to find the corrected value of gravity. So this is, we are adding the value. Positive correction. On the other hand, due to the valley, if I would fill this valley over here with the same material as over here, it will attract more the gravimeter towards downside. Because it is not there, I am getting the less gravity value. Again, I have to add over here positive correction. So the terrain correction is always positive. This is the only correction term which is always positive. This question also comes very often. Huh? They will ask you which correction term is always positive. So I'm always adding the gravity values, whatever correction values I'm taking out. So basically, what is the aim? My aim is to negate the effect of the terrain, this topography. Due to this undulation, how much gravity difference I am getting. So now the terrain effect is gone, the valley and the hill effect is gone. I have now a flat land. This is not the practical thing. The flat land is not there. It is still the mountain and the valleys. But you have neglected, or you have already compensated for the effect of the gravity due to the mountain and due to the valley. So you can treat this area as a flat surface. Now this flat surface is again at some height from the datum plane. If I will go vertically, exactly vertically down now, suppose let's say I am going exactly vertically downwards. Let's say this point over here. This is my theoretical value of gravity. It will give me, because this is a reference spheroid over here. Here I'm measuring the value, adding the correction term. First, I added some correction term, that is a terrain correction. I'm writing del GT. So I'm adding the terrain correction first. And now my surface is now behaving like a smooth surface. But between this point, let's say this is the A point, this is the B point. Between A and B, there is a mass involved. This mass is again trying to bring the spring towards itself. The extra mass between the datum plane and the station. To remove the effect of the mass, I have to subtract some value in this case. Why? Because the value of G that is measured is actually more than it should be, isn't it? Now, what is my purpose? Once again, my purpose is to find out. I will try to go as close as to possible to this GT value. Then I will see whatever difference that must be due to some kind of anomaly, some kind of objects present over here. So to approach this theoretical value, I have to compensate for lots of factors. First compensation was for the terrain, that was always positive. Now, because the station now is above the datum plane, it is you can see the gravity value at A. Let's say over here gravity value at A. This is gravity value at B. The gravity value of A will be simply greater, no, because more mass is there. More mass means more gravity value. So I have to neglect to equal this GA and GB. To compare this GA and GB, I have to reduce this effect of the mass. That is called as the Booger correction. So Booger correction, it is negative when the station is above the datum plane. And it is positive when station is below the datum plane. This is the Booger correction, and there is a formula for the Booger correction. The Booger correction formula is given by 0.041 into 0.042 specifically. I can write it as 0.042 into density of the mass present in between the station and the datum plane, milligauss per meter. (0.042 into rho or density milligauss per meter, and upper crust density is almost 2.67. I am doing this in the upper crust now. The survey is done in the upper part of the crust. If I will put the 2.67 value over here, the value will return as 0.112 milligauss per meter. Either I will add it or I will subtract it based upon the location of the station above or below the mean sea level or below the datum plane. For example, if I have the station over here, I am standing over here, the datum plane passes over here above my station, the reference spheroid passing over. It's a theoretical thing. It is nothing on the roof. Theoretical surface. Suppose this is my A point, this is my B point over here. So here, suppose my measured value is X. This is below the datum plane. This is the datum plane. Station is below the datum plane. That means I have to add some value. That means I will X plus 0.112 milligal per meter I will add. So I can know this distance. How much meter is this? Let's say this is 10 meter distance. So I will multiply 10 with 0.112 into 10, because this much is per meter. In for 10 meter, how much variation? This is this into 10. So I will add x plus 1.12 milligal. This will be the corrected gravity value at A. Had it been above the mean sea level, so for example, my station is above, this is the station, I am measuring the gravity value over here. This is the datum plane. Datum plane over here. Here I have to subtract the value. Suppose my measured value is x. I have to minus this 0.112 milligal per meter value. If this height is, let's say, 20 meter, for example, what will I do? It will be x minus 0.112 milligal into 20. This much. I will subtract. You know. So I added the terrain correction terms. So my measured value, whatever I measured using my gravimeter, I added the terrain correction. I am writing del GT. I am either subtracting or adding the Booger correction value, del GB, let's say. In different condition, I will either I will add or either I will subtract. Same. Next is the free air correction. It is exactly opposite to the Booger correction. It is because of the distance. We know that G is equal to Gm by R square. We neglected the effect of the mass. Now I have to neglect the effect of the distance. So now when I'm discussing about this, in this picture, I compensated the gravity value with the theoretical gravity value, which was, the extra gravity value at the A due to the mass effect is completely gone. The effect of the mass is completely gone. Now, only thing that is between the A and B is a distance. This much distance. Suppose that distance is R. Due to this distance, we might have different gravity values at A and B, because the B location is closer to the center of the Earth. A is farther from the center of the Earth. So the distance difference can create this difference in the gravity value. How much difference is created? That is called the free air correction. Now, because this A location is farther from the center, the gravity value is coming less. So if I will neglect this distance, the gravity value of this one and this one should be equal. That is called the free air correction. This is exactly opposite to the Booger correction. Booger correction is negative above the mean sea level or datum plane. It is positive when the station is above datum plane. It is negative when the station is below datum plane. The free air correction. Please once again explain the terrain correction. Okay, I'm explaining. Just let me complete this one, and I will once again explain the terrain correction. So what kind of measurement I'm doing? Measured value plus the terrain correction, which I will explain a little bit later. Terrain correction del GT. Then I either add or subtract the Booger correction value based upon its position with respect to the datum plane or the reference spheroid. I can write now del GF. That is, you can see the signs are completely opposite. It is positive, it is negative. That means when the Booger correction is positive, free air will be negative. When the free air will be positive, Booger correction will be negative. So this is how the two are The two are combinedly called as the elevation correction. So Booger correction plus the free air correction is called as the elevation correction. The free air correction equation or the formula, it is given us. .3086 milligauss per meter. 0.3086 milligauss per meter. So my combined elevation correction or simply elevation correction will be how much? It will be free air minus Booger. Combined effect now. If Booger correction is negative, free air must be positive, or I can take vice versa. Plus free air minus Booger, or I can write minus free air plus Booger. How much is free air? 0.3086 milligauss per meter. Minus how much was the Booger correction? 0.112 milligauss per meter. This is plus, this is minus. Somewhere around 0.2, you can calculate milligauss per meter is the combined elevation correction. Either this will be added or subtracted. Clear? Let's say we have a location A exactly below the location B. This is the station. This is the datum plane. Suppose this distance is 20 kilometers, for example. Okay. So what will I do? I will now try to find out what is the Booger correction and free air correction, the combined effect. This station is above the mean sea level or datum plane. That means Booger correction is negative. This is the Booger, and free air is positive. Over here, I have the formula 0.3086 milligauss per meter is the free air correction. So per meter it is 0.3086 per 20 kilometer. 20 kilometer is 20,000 meter. That means 0.3086 into 20,000. This much milligauss is the free air correction will be applied at this particular point. How much is the Booger correction? 0.112 milligauss per meter. No? So I can write 0.112 into 20,000 milligauss per meter. But one of them is positive. Which is positive? The free air is positive. In this case, Booger is negative. So I will subtract this from this. I can write the corrected gravity. In this case, corrected measured gravity is 0.3086 into 20,000 minus 0.112 into 20,000. The unit will be in the milligauss. This is how we apply the free air and the Booger correction. So Lakshmi is asking to explain the terrain correction once again. The terrain correction was basically done to neglect or negate the effect of the terrains. Let's say we have a mountain. Suppose this is Himalaya. Let's say this is Arunachal Pradesh. This is the Assam basin, for example. I am just doing the survey over this location. This is my gravimeter. I am doing the survey. Let me draw this diagram a little bit bigger. Let's say we have the Assam basin. This is the Arunachal Pradesh, for example. I am measuring the value of the gravity at this location. This Himalayas in the Arunachal Pradesh, they have some mass, no? If that mass is, let's say, h, for example, the gravimeter had some mass, let's say that mass is small m, it will attract the gravimeter towards itself, no? Let's say you have the weight machine, all of you measure your weight, no? You have the weight machine like this, and in this place your digital weight board will give you suppose 50 kg of weight. Suppose my weight is 50 kilogram. I am standing on this weight machine, 50 kilogram will be written in the bar over here. But suppose my friend comes, he lifts me little bit upwards, little bit towards upwards. What will happen? The weight measurement, what will I will get would be less than 50 kilo now. Suppose I get 49 kilogram. I'm weighing. That means what? My friend is applying 1 kg of force upside. Clear, no? Lakshmi, you're getting this, no? Suppose you are standing on the weight machine, your weight is 50 kilogram. Your friend comes from behind and lifts you upwards. Now your weight measured in the weight machine will be less than 50 now. But this is not your actual weight. To know your actual weight, I have to add this 1 kg. That is the correction term. So this is how the terrain correction is positive. So I am adding some terrain correction over here. Clear now? Understood, Lakshmi, this part. Similarly, here suppose there is no mass. It is completely a valley. No mass in this place. Due to this lack of mass, the G I would have got over here is less. If I will fill this area completely, now my G value will be corrected. What I want to know, I want to remove the terrain effect. For example, remove this terrain effect, make this land completely flat. So I calculated my effect of the higher parts. Now I will calculate the effect of the valleys. So when I will calculate the effect of the valleys over here, because there is no mass in this place, I am getting less gravity. For example, let's say you are standing on the weight machine and you put one of your foot down. You are only standing in 1 foot. Your weight measurement will come a little bit less now. Why? Because your 1 foot is not on the weight machine. So because there is no mass, the G I would have got, I am not getting that. So I have to add some extra value. So both in the case of the Himalayas, both in the case of the valleys, I have to add the correction terms. That's why the terrain correction is always positive. Always positive. Okay. This was the terrain correction. Similarly, we have the latitude correction. Latitude correction, and the formula is 1.30. Sorry, not 1.30. This is in mile. I will give it in kilometer. Much important. 0.811 sine 25 milligal per kilometer. Because we know with latitude my G value also changes, isn't it? With latitude my G value changes. So this is given as del GL by del S is equal to 0.811 sine 25 milligal per kilometer. What is del GL? This is equal to latitude correction. What is del S? This is the north-south horizontal distance. For example, let's say we are standing on a particular latitude. This is the Earth. I am standing over here. My first measurement was here. I am going to the second location. This is suppose A. This is B. I am going to the second location. How my gravity will vary? It will increase or decrease, guys. From A to B, the gravity value will increase or decrease. Answer quickly. from A to B, my gravity value will increase or decrease? From A to B, it will increase, no? Because I'm going from pole to equator, isn't it? So towards the equator, the gravity value increases, no? So how much is the distance between A and B, horizontal distance? This much distance I covered from A to B on the surface of the earth, and this much gravity value increased. So to correct that, del GL, that means latitude correction by del S, will be given as 0.811 sine 2 phi. No? It will not decrease, Lakshmi, it will increase, no? At the pole, the gravity value is more, maximum. At equator, it is minimum. So I am going from minimum position to the maximum position. The value will increase, no? Okay. Next. Next is my drift correction. This is a little bit lengthier process. The drift correction. The drift correction is basically done due to the creep in the spring itself, because we know that gravimeters, they use the springs. If they are repeatedly used or due to the effect of the temperature, the spring length can itself vary. No? For example, it is you are doing measurements in a hot region. With increase in temperature, it will increase the spring length because spring is made up of metal. No, or in the winters, the spring length might decrease. That can affect your measurement. No, you need your instrument much more sensitive. That's why we use the drift correction. Now we have discussed in the class all these things in much more detail. Those who are our students, they can understand quite easily. The drift correction is basically done with respect to the station. So we have a station, we call it the base station. At this location, I know the exact gravity value. Then I do the measurements at location 1, location 2, and location 3. Then I will again come back to the base station and take the measurement again at the base station. The first measurement at the base station, then I'm going to the location 1, location 2, location 3 to measure the gravity value. I'm again coming back to the base station. So I'm going from here to here to here, then again coming back to the base station. Then I will go straight to the location 4, 5, 6, here and here, again come back to the base station. Then again I will go to the 7, 8, 9, this kind of location, and again come back to the base station. So in regular interval, I have to come back to the base station to check has the spring length decreased or increased. Then I will put a graph. Time and G value, how much extra measurements I'm getting. So suppose this was my base station value when my time was 0. First base station value was here. Suppose second time when I came to the base station, the value was G value was here. The third time the G value was, suppose, let's say here. Now I will connect these 3 curves. They're the base station surveys. Let's say we have location 1, 2, 3, 4, 5, 6. These much locations we have. So first we measure in the base station. Then again after 3 we have again base station. Again after 6 we have the base station. Base, base, and base. So this is the same. This is base 1. Let's say base Roman letter 1. This is Roman letter 2 and 3. So this is the base 1. This is the base 2. This is the base 3. This line is called as the drip line. No, but this should not have happened. No, the baseline should be flat. No, under normal circumstance, it should be a flat surface. Whatever the value of the gravity at base location should be always equal. No? With time also it should always equal, but it is not remaining equal because there is small change in the spring length due to temperature, tidal effect, and we correct this. This is the baseline. This is the drip line. This amount, suppose I want to know after suppose 1 hour how much change I have or how much correction I have to apply. I will just take a vertical line over here. The difference between the drip line and the baseline is my correction term. So suppose after half an hour, my measurements were like this. How much correction term I will apply? This much correction term. This is called the drip correction. So they will not give you the example numerical as such in this section, but they will ask you which is the drip line, which is the baseline. You know the drip line, you know the baseline. Similarly, we have the Eötvös correction, which is very, very important. The Eötvös correction is commonly used in mobile gravity survey. When the gravity is surveyed in a mobile platform. For example, if you are on the Earth surface, you are doing the gravity survey. Let's say we have the Earth like this. This is the equator, for example. Let's say you are coming from China. This is suppose China. And we are coming to, let's say, Europe. Doing the gravity survey. You are moving in which direction? In this direction? No. This is east. This is west. We are moving from east to west when we come from China to Europe. Now tell me, what is the Earth's rotational direction? Earth rotates from west to east. The Earth rotates from west to east. Now here the relative velocity term comes. Suppose this is a bus. The bus is going with a velocity v1. You are standing over here, you are running with a velocity that is v2. So your velocity with respect to the ground will be equal to v2 plus v1, isn't it? Yeah, the relative velocity. And in this case, it is the opposite thing. No? So any place on the Earth, let's say any place on the Earth, this is the equator. Suppose let's take this point. This point is also experiencing a centripetal force and centrifugal force. The centrifugal force will be acting outwards because this is the rotational axis over here to around which the Earth is rotating. Rotational axis. The centripetal force will be always away from the axis. This is the centrifugal force. Who is balancing it? The gravity. Gravitational force. Suppose you are standing over here. Due to the Earth's rotation, the centrifugal force is trying to push you away to the space, but the gravity is holding you back. Now they're in equilibrium. That's why you are stable in this particular location. You know? So we have G, that is gravitational acceleration. And we have A, that is centrifugal acceleration. They're opposite to each other. G and A are opposite to each other, no? And if you are moving from east to west on the Earth's surface, you are moving against the Earth's velocity. The Earth is moving what? This is you moving. This is you. Earth is moving from west to east. This is Earth. That means if the Earth is a train, for example, moving from west to east in this direction, you are the person moving in opposite direction. Earth has a velocity v1, your velocity is v2, the net velocity becomes v1 minus v2. Because the velocity is decreasing, the acceleration will also decrease. If the acceleration decreases, in this diagram, so we have the centrifugal acceleration. I can simply write centrifugal acceleration. And this is gravitational acceleration instead of force. If the centrifugal acceleration is decreasing, what will happen to the gravitational acceleration? It will increase. No, that means if you are moving from east to west, like China to Europe, I gave in the picture, your G value measurement will become more. So while moving from east to west, measurement of G is more than the actual value. If this is the case, what we have to do? We have to subtract some value. That means subtract some value. Negative correction. Because I'm getting more G value than natural. Negative. But if I'm moving from west to east in the direction of the Earth's movement, so this is the train moving at a velocity v. You are moving at a velocity v1. The velocity will add up because both are moving in the same direction, v plus v1. When velocity is increasing, because addition, acceleration will also increase. That means centrifugal acceleration will increase, gravity value will decrease. So G value will come less. Measured G value will be less than the actual G value. So what have to do? You have to add some substance or positive correction. So west to east positive correction, east to west negative correction in the Eötvös. This is called the Eötvös effect. Only in the mobile parameters when you're moving from one part to another. Okay. So these are the different correction terms we use in the gravity measurement. After doing the corrections, so we have the measure correction. We have the measured gravity. We applied the correction terms. Which correction terms have applied? Terrain correction, Google correction, free air correction. What else? Latitude correction. No. Also Eötvös correction. These are the correction I'm applying with the measured value. After applying all these corrections, I will compare it with the theoretical value. This will be same now. I have tried to bring the GM value or the measured value as close as to the theoretical value by applying these corrections. But still there is some difference, that is the gravitational anomaly. So we have corrected measured value, suppose that is GM dash. and GT is the theoretical value, and my anomaly would be equal to Gm dash minus GT. Basically, two major anomalies we discussed. One is the Booger anomaly. Another is the free air anomaly. The Booger anomaly is basically the major gravity value plus minus the Booger anomaly minus plus the free air anomaly plus the terrain correction. Sorry, correction, Booger correction, free air correction, and terrain correction minus the theoretical value. This is the Booger anomaly. The free air anomaly, we do not count the Booger correction. So Gm minus plus the del Gf plus the del Gt minus the theoretical value. So in the Booger anomaly, we are considering the Booger correction. In the free air anomaly, we are not considering the Booger correction. That is the only difference. Why we need two anomalies? This free air anomaly is commonly used in the ocean surface, in the oceanic gravity survey. This is found in the oceanic gravity survey, the free air anomaly. Because when you're going in the ocean, suppose you are in a ship trying to measure the gravity value, this is the ocean floor. From the station, this mean sea level is itself a datum plane. There is no mass between the station and the mean sea level. There is no point calculating this Booger anomaly. You know, because this is the station, this is the mean sea level. We're measuring on the datum plane or the mean sea level. That's why we do not calculate the Booger anomaly in the oceanic gravity survey. We use the free air anomaly. Now coming to the instruments, let's quickly discuss the instruments, gravimeters. We have two types of gravimeter. One is stable, one is unstable. The stable gravimeters, they use both of them, they use spring, so they are without any restoring force. But the unstable gravimeters are with restoring force. Okay. This is the only difference. For example, let's say we have a spring, a mass is attached. Suppose this mass is m. What kind of force is experienced by this mass? Mg downwards. This will be exactly equal to the spring force, that is equal to k into k is the spring's constant into the displacement in the spring. So Ks would be equal to mg. That means the spring's constant into the displacement in the spring will be equal to m into g. Suppose the g value increases. That means my force become m g plus del g. That means my spring length will also increase. It will be k s plus del s. And we try to find out how much is the change in the gravity value, because we know this much, how much change has happened. We can measure in the spring length. Original spring length is known, k is also known, m is also known. We can calculate what is this del g over here. This is the basic concept of the stable gravimeters. In the unstable gravimeters, however, we have a restoring force which will keep the gravimeters in a perpetual movement. For example, let's say we have spring attached like this. a mass is attached over here. Let's say M. With increase in G, this mass will go downwards. This mass will move downwards if the G value increases, because it will experience more force. What will happen to the spring? The spring will increase in length like this. And from this, I can find out what is the change in gravity over here. No? The unstable gravimeters are commonly asked in the questions because they are the gravimeters which are used in the modern surveys. So we have Warden's gravimeter. We have Lacoste-Rombaud gravimeter. They are the two basic gravimeters we use in the. Also, we have the Thyssen's gravimeter. Three common gravimeters we use in the. Guys, can you hear me and see me? Am I audible and visible? Am I audible and visible, guys? I hope I'm audible. Huh? You can hear me and see me. Okay, cool, cool. So these are the common gravimeters we use in the field. So they have different sensitivity. That means how much, how precisely they can calculate the gravity value. It can be called as the sensitivity of the gravimeter. And the Lacoste-Rombaud gravimeter is the gravimeter which is the first gravimeter to use the zero length spring. This is the first gravimeter to use zero length spring. Okay. The last part in the gravity chapter would be our isostatic anomaly. The isostatic anomaly is given as the gravity anomaly minus desired effect of the root. We will explain this thing. Let's take a break of 10 minutes, and after this we will discuss the isostatic anomaly and we'll go to the next chapters. Okay, let us continue. Lakshmi is saying, sir, please explain unstable gravimeter. So in the what is the difference between the unstable and stable? Let me start the recording. Lakshmi is asking about explaining the unstable and unstable gravimeter once again. So the basic difference is, in the stable type of gravimeter, what you do, you have a spring having mass m. Suppose this is at a location, that location is A over here. I brought the same machine to another place, that is B. Suppose here the G value increased. What will happen to the mass? The mass will come little bit down. No? How much increase in length happened? You can calculate the increase in G value. But in the unstable gravimeters, there is a restoring force. What is the restoring force? For example, let's say we have different gravimeters. I'm not going into detail because we have lots of other things to cover. Suppose something like this I have mentioned. This is a spring attached over here. This is the fixed end. This is the movable end. And this is the mass. So when I am bringing this machine to another place, suppose where the G value is increased, this part of the arm, it can move, it can go down. No, from this to this, because more G means more force, it will go down. What will happen to the spring? The spring length will increase like this. But once it is going down, this fixed end will try to drag back the spring to its side. The fixed end over here, it will try to drag the springs back to its own side. So now what will happen? Again, it will go up. Again, the gravity will try to bring it down. So it will be in a perpetual motion. It will go up and down, up and down. So you can get the time period from here. From the time period, you can calculate the gravity value, the change in gravity value. The basic mechanism of the unstable gravimeters. Anyway, we are discussing about the isostatic anomaly. This is the formula: gravity anomaly minus the desired effect of the root. Now here we have to know about the isostatic theory, like Airy's and Pratt's theory. So basically, if we have a mountain, let's say we have a young mountain, newly formed mountain like Himalayas, there should be a root according to the Airy's theory. There should be a root, and the root length should be, or root height, this much is a root. So we can calculate, we have the formula, no, to calculate the root. There is a definite formula to calculate the root. But since it is a newly formed mountain, the root is not completely formed. Suppose the root is not completely formed. So in the mountains, I will generally see the negative gravity anomaly. Why? Because we have the roots going downwards over here. This is mantle. This is mostly the crust. The crust is moving downward. So we can find the lateral density variation. For example, here, the density is equal. Density is equal. Density is equal. But once I'm entering into the mantle, high density, mantle has more density, but now low density material is coming. Again, high density. So above this point, I will find negative gravity anomaly. So I will get what? Negative gravity anomaly in this case. Negative gravity anomaly. Okay. Same concept over here. If we have let's say we have the mid-oceanic ridge, for example. The mid-oceanic ridge will look like this. The mantle material is coming upside. This is the mantle coming upside. So here the lava is coming out, the basaltic lava or the more mid-oceanic ridge basalt. If we will plot my gravity profile, here we have this is the crust, this is the mantle. The mantle is coming upwards. There the crust was going downwards. That's why negative gravity anomaly. Here the mantle is coming upwards. So in the zone of low dense material, that is crust, we have high dense mantle present over here. You know, that's why it will show this positive gravity anomaly. So based upon the lateral density variation, we can find out the different gravity anomalies. So suppose I have a massive ore body inside the Earth surface, let's say, and I am measuring my gravity values over here. This massive the ore body has lots of density, so high density. Let's say that is rho m. The surrounding density is suppose rho c, and rho m is more than rho c. I will get this positive gravity anomaly above this. That's why I try to explore the different ore bodies. Next, suppose we have a petroleum deposit. This is you standing over here. That is petroleum deposit. Suppose there is an anticlinal trap, and we have the petroleum deposits over here. Petroleum is less dense. So what kind of gravity profile I can see? Negative gravity profile. The gravity profile will go down. Negative gravity anomaly I will see because the density of the petroleum is not very high. It is very, very low. So why do I use the gravity survey? To find out the basically massive ore bodies like chromites, for example, chromite. We can also use them for the massive sulfide. But massive sulfide is commonly seen in the cell potential, but we can also use the gravity. Gravity can be used everywhere. Sulfides, we can use them for the petroleum deposits. We can use the gravity survey for these ore minerals. Next, let's quickly move to the next chapter, that is the electrical chapter. Electrical chapter, it is based upon the law of electrostatics. There the law is equal to this K U1 U2 by R square. Same, the inverse square law. Suppose we have a charge Q1, another charge Q2, separated by R distance. The force of attraction between them is K Q1 Q2 by R square. You can write in the vector form. It will be equal to minus K Q1 Q2 by R square into the unit vector, where K is the Coulomb's constant. And it is taken as 1 by 4 pi epsilon naught, where epsilon naught is called as the permittivity. Permittivity. Let's say we have a positively charged ion, we have a negatively charged ion. They will attract each other. Let's say this positively charged ion is attracting the negatively charged ion. That means it is applying some kind of force. Not all the force is reaching the negatively charged ion. Some is absorbed by the medium. To suppose this is my vacuum. I am doing this in the vacuum, this experiment. The vacuum medium will try to absorb some of the force. Suppose 10 units of force is applied by the positively charged ion towards the negatively charged ion. But not all the 10 units will reach. Suppose 8 is reaching, 2 is absorbed by the vacuum medium. That is called as the permittivity. So basically, what is permittivity? Force absorbed by medium. Okay, that means my force will be always inversely proportional to the permittivity. Let's say I'm doing the same experiment in the water. Suppose we have a water medium, we have the same positively charged ion and negatively charged ions are distance apart. How much is the force over here? 1 by 4 pi epsilon W, that is permittivity in the water, into Q1 Q2 by R square. Suppose Q1 is the magnitude of the positively charged ion, Q2 is the magnitude of the negatively charged ion, it will be Q1 Q2 by R square. That is something called as the relative permittivity. Unitless, because it's a ratio between the two permittivity, which is equal to the permittivity of a medium divided by permittivity in the vacuum. That means I can write as relative permittivity as permittivity in a medium by permittivity in the vacuum. For example, in this case of water, I can find out the relative permittivity of the water is equal to permittivity in the water divided by the permittivity in the vacuum. Okay. That means my permittivity in the water will be equal to how much? Permittivity in the vacuum into relative permittivity. So I can replace this in this equation over here. I can write force is equal to, in the water itself, 1 by 4 pi epsilon naught epsilon r u1 u2 by r. Instead of epsilon w or permittivity in the medium, I have written epsilon naught into epsilon r. This is the laws of electrostatic. Unit of Q is coulomb, and 1 coulomb is 1 ampere into 1 second. So 1 coulomb is 1 ampere into 1 second, ampere second. Similarly, as we have the gravitational field, here we have electrical field. The electrical field will be given by E is equal to 1 by 4 pi epsilon naught Q by R square. This is force per unit charge. Or I can write Q1 by R square. For example, we have Q1 charge and Q2 charge where R distance apart. The force was equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. If I will make the Q2 1, it will be Q1 by R square. That will be my electric field. That means force experienced by unit charge. Similarly, I have potential energy, electrical potential energy, which is equal to force into displacement. It will be equal to how much? 1 by 4 pi epsilon naught Q1 Q2 by R. Just compare with the gravitational potential energy. It was what? G m m by R. No. Similarly, this is K Q1 Q2 by R. Same logic itself over here. Similarly, we have potential, electric potential, which will be equal to 1 by 4 pi epsilon naught Q1 by R. My gravitational potential was what? Gm by R. Remember? This is K Q1 by R. The force, field, potential, energy, potential. It will be exactly identical. Whatever we have this in the gravitational field, same in the electrical. Similarly, we have equipotential surface. There it was independent of mass. Here it will be independent of charge. No? And suppose we have a charge Q1. Around this, we have multiple equipotential surfaces. Infinite number of equipotential surfaces I can draw. Between this and this, there is a potential difference. So if I will put a current over here, it will try to come back to here. High potential to low potential. That is called the potential difference. And the unit is volt. Potential difference. Unit is volt. Inside the earth, we can use multiple types of electrical methods. There are some natural electric source methods. And we can get induced electrical source. Natural electric source and induced electrical source. Natural electrical source, it uses the inherent electrical property of the earth. Whereas induced electrical source, it uses external electrical field. If I want to measure what is the electric field inside the earth as it is the natural electric source I'm measuring. What is the electric field in the earth? What is the potential difference in the earth? That is the natural electric source. Whereas in the induced electrical source, I will apply some external current inside the earth and I will see how the current is moving from one part to another. And based upon that, I will do my interpretation. The natural electric sources are self-potential method. And induced. Self-potential method or spontaneous potential. We have telluric current. We have magnetotelluric. We have audio frequency magnetotelluric, AFMAG. Audio frequency magnetotelluric. In the induced, we use the resistive method, resistivity. And we use the electromagnetic method. And we use the IP method, induced polarization method. Induced polarization method. So natural and induced electrical source. So first we'll discuss about the natural electrical sources. In the natural electrical sources, first we'll discuss about the self-potential method. Self-potential or spontaneous potential. These are the inherent potential differences found inside the earth. So now we'll see inherent potential difference and inherent conduction inside the earth. First, let's see what are the inherent conductions happening inside the earth. Natural conductions inside earth. What are they? They are ohmic conduction, then there is semiconduction, then there is electrolytic conduction, and dielectric conduction. These are the four conduction types we see naturally inside the earth surface. This ohmic conduction is basically based upon the Ohm's law found in the true conductor. So ohmic conduction it obeys the Ohm's law. Which is equal to V is equal to IR. No? The Ohm's law says potential difference is equal to current into the resistance. And we know resistance is equal to rho L by A, where R is the resistance. The unit of the resistance is ohm, given as this symbol, and rho is the resistivity, and the unit is ohm meter. 1 by resistance is called as the conductance, and 1 by resistivity is called as the conductivity. Conductance is given as a symbol sigma, C, and conductivity is given as the symbol sigma. The unit of the conductance would be ohm inverse. And the unit of conductivity would be ohm inverse, meter inverse. No. This is conductivity. This ohmic conduction happens in the true conductor. So whatever ionic or metallic particles are inside the rocks, when the current passes through these metallic particles, they will go or they will obey the Ohm's law. The Ohm's law is only obeyed by the conductor. For example, the gold, silver, iron, they will obey the Ohm's law. Next comes the semiconduction. What is semiconduction? Here the conduction is little bit slow than the ohmic conduction. This is externally induced conduction. That means you are using these solar shells, no? So using temperature, suppose I will heat the rock and the conduction will carry on. That is called the semiconduction. So you must have heard about this PNP, NPN semiconductors. You must have studied in the school days. Suppose I have a semiconductor. This is the sun. The sun ray falls on the semiconductor. The sun ray is giving some energy. That energy will excite the electrons. What will happen? The electrons will move from one part to another after excitation. it will leave its own place. When the electron is leaving its own place, at that particular place, a positive charge is created because electron is leaving that place. And that's how the charges are created. We call them the holes. These electron leaving areas are called as the holes. And consequently, the electricity carries on from one part to another. This is called as the semiconduction, which is commonly used in our solar cells, your batteries, lithium batteries, which you use in mobile phones, they're based upon the semiconduction. Also, the signal inside the microchip, no, this Snapdragon 8th generation chips, no, whatever chip you see, they're basically semiconductor, where we have semiconduction happening. We are giving some external energy that is exciting the electrons. It is moving from one part to another, and electricity is carried out. Similarly, we have electrolytic conduction. Here, the ions are carried by the fluids from one part to another. That's why the electricity is flowing. Suppose we have groundwater flowing from one part to another. Groundwater has lots of ions dissolved in it. Basically, groundwater is taking the ions from one part to another. While doing so, the charges are moving, and whenever the charges will move, an electric field will be generated. So these are produced due to movement of ions aided by fluid movement. We call them the electrolytic conduction. Last but not the least, we have dielectric conduction. Where the conduction is happening in the insulators. This type of conduction is very, very low, commonly found in the insulator. For example, the mica, muscovite, it is very, very, it has a very, very low conduction or low conductance. It will not carry electricity as effectively as other metal or other minerals. They're called the insulators. We see dielectric conductions in the insulator. Next, we will discuss regarding the spontaneous potentials, the natural potentials inside the earth. There are natural currents, natural potentials. But I will stop it over here. I will have another session of this webinar in the next week, and please attend those to follow all the rest of the chapters. It is difficult to cover all the chapters. It's a huge chapter. I am trying my best to cover as much as possible, but we will see in the next chapter or next webinar. We will discuss all the rest of the things, and we'll do some questions and how to solve the questions. That is much more important. Any doubt from today's chapter, whatever we discussed? Anyone? Anyone has any doubt? No doubt. Okay, then see you in the next week. We will send this in the Telegram channel. Please be attentive, and we will have another session of the webinar when we will discuss the rest of the chapter over there. Thank you. See you in the next week.